I'm going to talk today about, okay, so what happened is that in the 90s there was this Cryptosystem called Chor-Rivest that has been a little bit forgotten, and what I'm going to show to you is that inside this Cryptosystem there is something nice in terms of information theory, or at least coding theory. So more precisely, I will show you a lattice which has a packing which is very close to Minkowski bound, and for which we can solve the bounded distance decoding problem efficiently, meaning in polynomial time. So this is joint work with Cécile Pirot from last year, and it's been published at Design Code and Cryptography. So when we look at modern lattice-based cryptography, what we do to be sure that everything is secure is that we use random lattices, lattices that have no structure at all. And for those lattices, we can prove that it is as hard to break them as breaking the worst case lattices. So this is very nice. This gives us a lot of confidence, but that's not how it has always been in lattice-based cryptography. When you look before the 90s, what were done in lattice-based cryptography, well, people were a bit more sketchy, and they didn't figure out how to do it, so they were trying to build special lattices for which we know how to decrypt. We have some kind of hidden structure that can be used as a secret key. And so they were not calling it lattice-based, they were calling it knapsack cryptography or subset sum cryptography. And that was a total disaster. Almost all the schemes ended up broken. So actually, if you look in more detail at the literature, there's one exception to this, the Chor-Rivest Cryptosystem. So as far as I understand, it's still not fully broken. There is an attack that is sub-exponential, but that's it's not enough to destroy it. And despite this attack, which forces you to take larger parameter, this cryptosystem has impressively compact ciphertext when you compare it to modern lattice-based cryptography. So how come that it has such compact ciphertext? Well, when we look at modern lattice-based cryptography, so what happened is that before doing the encryption and decryption, on top of this, there's an encoding phase and a decoding phase. And except maybe that for the scheme that was mentioned in the previous talk, LAC, most modern lattice-based cryptography handle this coding and decoding phase using the naive lattice ZN. So there's basically no encoding. We're just using coordinate-wise rounding to decode things. So you can imagine as a code theorist that it is not very efficient. And when you look at what's happening in Chor-Rivest at the decoding phase, well, this is much more involved. So this is what we're trying to figure out in our work, what's going on behind Chor-Rivest cryptosystem. And we do so by, well, removing the crypto from this cryptosystem. And what we'll end up having is a dense lattice packing for which we do have an efficient decoding algorithm. So by efficient, I don't mean that you can efficiently implement it on a chip. I just mean that it is polynomial time. And by dense, I don't mean that it is dense in practice. I mean it as in an asymptotic sense, as we will see. So I'm sure you all know this, but I just want to make it clear, especially because maybe people are more used to working in the Hamming metric over binary field. I'm working in a Euclidean space with a Euclidean metric. And so one of the problems that is very old in mathematics, you can date it back to Kepler, I think, is the dense lattice packing problem. So your goal is to find this arrangement of sphere that kind of maximize the minimal distance between 2 points, so that you can draw very large balls around each of those points with those balls barely touching. So of course, because I can scale up and down the lattice, I'm going to fix the volume of the lattice, and I want to maximize this minimal distance under this volume constraint. So this is a purely mathematical question, but there is also an algorithmic question that kind of goes with it. It's like, once I have a nice packing, can I do decoding? So decoding is the following task. I'm given a point t in space, and I have the promise that it is a lattice vector v plus some small error e. And my goal is to recover either this vector v or equivalently the error that has been added to it. So for this problem to have a unique solution, it is necessary that the radius of my errors is at least is at most half of the minimal distance, but I might be interested in solving this with a slightly smaller radius. I just want this radius to be as large as possible and to have an efficient algorithm for solving this bounded distance decoding problem. So let's look at what is known in terms of lattices, packing and decoding algorithms. So as I mentioned, there is this trivial way of doing things, which is pretty much don't do any clever encoding. So just use a lattice Zn that correspond to just doing coordinates by coordinate rounding. So that's a nice lattice algorithmically in the sense that it is constructible. You can construct the basis. That's pretty trivial. The identity matrix, and you can solve BDD efficiently in it. You just round each coordinate. But that's not very nice because we're so far away from the optimal. Indeed, it achieves minimal distance of 1, whereas actually for a lattice of dimension m, we would like to reach Minkowski bound. Minkowski bound tells you that it is at most square root of n, and we would like to reach this. So other lattices, we can use random lattices. And for random lattices with high probability, we're going to have a very large minimal distance of essentially square root of n. And it is very easy to construct random lattices. The problem is that we don't have any algorithm to solve BDD efficiently in those lattices. And this is actually why we can build cryptography based on lattices, because on random lattices, solving those problems is hard. This is our basic assumption to build cryptography. So maybe let's look at other lattices for which that have good packing. So there are other lattices either coming out of algebraic geometry for the Mordell-Weil lattices or from number theory for the Martinez lattices. Mathematically, they're known to reach this bound. The problem is that actually algorithmically, I'm not even sure that we can construct efficiently those lattices. They have a mathematical definition, but if I have to fit them in a computer, I'm not even sure how we'll compute with those things. So even less so solve BDD on them. So maybe there's a trade-off, and that's called the Barnes-Weil lattices. In terms of construction, they really look like the polar codes. They're kind of iterative construction with tensor products. And for those, we can reach a minimal distance that is somehow halfway toward Minkowski bound, so the fourth root of n. And they're very nice, they're constructible efficiently, and there is also an efficient algorithm to solve BDD in them, given by Michenchu and Nicolaisi, I think. But we're still kind of far from the target. And what I will show is that with Chor-Rivest, we get much closer to the target. We just get a log n factor away from Minkowski bound, and they will be both efficiently constructible, and we will be able to solve BDD efficiently. Again, by efficient, I just mean polytime. I don't mean that I've implemented it. Actually, I'm going to show something even stronger. Here I've been talking about the Euclidean lengths, but actually the algorithm is more fit directly with the L1 norm. And I'm going to show that I can solve the bounded distance decoding problem up to a radius of n over log n for the L1 norm. And just by typical L1, L2 bounds, it will also mean that I reach this bounded distance decoding radius for the L2 norm. Okay, so to define them, I'm going to choose a modulus m, which is going to be a power of 3. I could have taken a power of 2 or power of something else, but 2 is painful for some reasons. 2 is not a very nice prime number, actually. It's even, and it's odd somehow. So let me take m equal to 3 to the n, and we're going to consider the multiplicative group modulo m. So all the non-zero, all the numbers that are not multiple of 3, and I'm going to consider this under multiplication law. And I'm going to take the first prime, except 3, because I've just taken it for another purposes. And I'm going to take n of them. So the largest one of them is going to be slightly larger than n, so n log n. So that's the first prime. And then I'm going to consider the group morphism that goes from this additive group Zn to this finite multiplicative group that sends a vector x1 up to xn to the product of the pi xi, all this modulo n. And my lattice, I'm going to define it as the kernel of this morphism. So all the set of vectors such that this product is congruent to 1 modulo m. All right, so that's a rather still mathematically abstract definition of the lattice. So why is it a lattice? Well, it's a subgroup of Zn, so that's necessarily a lattice. So one of the questions first, before showing you properties of this lattice, I'm going to convince you that I'm actually able to write down this lattice on a computer, or compute somehow a basis of the lattice, for example. So I'm going to choose G to be a generator of this multiplicative group. I'm going to call N the size of this group. So that's the Euler quotient of M. That's just this number here. So that's very close to M. And my claim is that mathematically I can rewrite this lattice as a subset sum lattice. So what I do, well, I'm going to take the logarithm of the previous equation, but the discrete logarithm. So I take the discrete logarithm of each of the pi in base G, and then I've just rewrite my lattice as this subset sum lattice. Okay? And my claim is that because I've chosen my modulus M in such a way, then computing those discrete logarithms, log G, log in base G of pi, this is an easy task. So I'm going to not give you the details of this algorithm. It's a well-known algorithm in number theory by Pauling and Hellman. But basically, the idea is that you can successively search for the discrete logarithm for increasing powers of 3. Okay? So you just do an exhaustive search modulo 3, and then you kind of lift it and search again among 3 possibilities, et cetera, and you're going to get your discrete logarithm modulo M. And so once you've been able to write your lattice explicitly like this as a subset sum lattice, you can also write explicitly a basis. That's very standard. All right, so now remember that I told you that I was supposed to consider lattices of volume 1, so I want to know by how much I need to rescale my lattice to have volume 1. So what is the volume of my lattice? Well, I'm going to claim that it is less than 3 to the n. This is rather elementary from group theory because I've defined my lattice as the kernel of this map. So the volume of my lattice cannot be, the volume of my lattice is the number of cosets it has over Zn. So in particular, it is smaller than the image of the morphism psi. So this is smaller than the size of this group. So, okay, so it is smaller than 3 to the n. So what does it mean? It means that I just have to rescale my lattice by about 1/3 to make its volume back to size 1, right? Because the volume is multilinear, right? If I divide by 3, then its volume decreases by 3 to the n. So essentially, I can already consider that my lattice is renormalized up to a constant factor 3. So let's just think that its volume is 1. All right, so now the real stuff. I want to show that this is a good packing. I want to show that its minimal distance is large. And I'm going to do this for the L1 norm, so that's what I'm denoting here. And I'm not going to do the full proof. I'm going to make a simplification. What I'm going to show you is that there are no vectors, no positive vectors, so vectors with only positive coordinates that are smaller than this in this lattice. No non-zero vectors like this. So remember the definition of my lattice. So that's a set of points that verify this equation. And the thing is that if I take a vector with positive coordinates and a non-zero, then for this vector to be in the lattice, it must be the case that this product wraps around modulo M, right? If I want this equation to hold, well, it has, and because this cannot be congruent to, this cannot be equal to 1, because that's only for the 0 vector that this is equal to 1. So if it is congruent to 1, it has to exceed M. It has to be of the form km plus 1 for some positive k. So in particular, it is greater than m plus 1. Okay, but remember that my primes pi, I've chosen them to be small. Okay, so for this equation to hold, for this inequation to hold, I need x itself, I need at least the sum of the coefficients of x to be large. So in other words, I need the L1 norm of x to be large. And this reaches our claim that at least for positive vectors, they must all be large inside the lattice. All good so far? All right. So that's nice. We have a lattice. It's a good packing. And the last task ahead is to show that we can actually do decoding in this lattice. And again, I'm going to cheat a little bit at first, and then I will uncheat in the next slide. But for now, I'm going to give you a decoding algorithm that only works for positive errors. And actually integers errors as well. I'm not going to touch non-integer errors in this talk, but you can see in the paper how it is handled. So remember that the bounded distance decoding problem is defined like this. I'm given a target T. It's written as a vector from the lattice V plus some error E. And my error is bounded by some radius R. And here R is equal to n over log n. All right. So the thing is, oops, no, it's not the right direction. OK. What I'm going to do is I'm going to take my target T, and I'm going to compute this product. F is equal to the product of the pi to the ti reduced mod m. So if I unroll the definition of f, I can rewrite it like this. Of course, I don't know vi and ei. But I know it can be written like this. And if you remember the definition of my lattice, well, if v is in the lattice, then this product here on the left, by definition, this product is congruent to 1 mod m. Okay? So it means that modulo m, there's only somehow the error part that is staying. But that's the nice thing, because we've assumed that both the pi and the ei's are small. The fact that I know this product modulo m, but I also know that it is smaller than m, so I can reconstruct it over the integer, not only modulo m. I know this result over the integer, not only modulo m. And then it becomes very easy to decompose this thing. You just have to factor it, and you recover the exponents ei, and therefore you recover the error and the vector. Okay, why is it easy to factor? Because I know that my number is composed only of those few small primes. So I can try to divide by each of them until I've completely factorized it. You know, factoring is a hard problem, but it's a hard problem only if you have no idea what the factors you'd like. If you know in advance that the factors belong to a small set, factoring is a very easy problem. All right. So last step I want to show is how you handle negative errors. So I'm going to make a slightly stronger assumption on my errors, but asymptotically this is still the same decoding radius. And I'm going to compute the same f as before. And this time in my mind again, I'm going to decompose it into 2 parts. The one with positive exponent and the one with negative exponent. So in my mind, I've used this as a fraction modulo m of u and v. And I know that u and v are both small. And because of this, I'm going to be able to do some rational reconstruction. So what is rational reconstruction? Well, it's pretty much, again, a lattice task. So somehow, what you can do is construct this lattice, which is a 2-dimensional lattice. So the set of all the integer x and y such that x minus fy is congruent to 0 mod m. And I know that u and v is a solution of, is a point in this lattice. It's a solution of this equation. But I know that it is actually the shortest non-zero solution because I have this bond on their length. And I can prove that because those solutions are so short, I can show that those are the shortest one. And so finding the shortest vector of a lattice is supposedly a hard problem, but that's only when the dimension is large. If you do it in 2 dimensions, that's a very easy problem. And I think Gauss already had an algorithm for this. But sometimes it's attributed to Lagrange. Okay, so we can recover u and v. And then we just have to factorize u and factorize v. And we recover our error vector e. All good? So just a few closing remarks. So this is what we achieved. We've found a lattice that is dense in the sense that its minimal distance is very close to Minkowski bound, just a log factor away. We have an efficient algorithm to construct it, meaning that we can actually write a basis of it in a computer. And we do have an efficient bounded distance algorithm for it. So what is it? So if you go back to the Chor-Rivest paper, you may find it weird because what they do in this paper doesn't look at all what we're doing here. I mean, the ideas of the construction are exactly the same, except that for simplicity, I found it nicer to construct things over the integers and integer mod 3 to the n. But what's happening in their paper works over polynomials over finite fields. But both construction actually achieve the same asymptotics and are exactly based on the same ideas. The rational reconstruction is slightly different, but that's essentially it. Oh no, actually they don't do rational reconstructions, they don't do negative error, sorry. But I guess this is feasible as well. So what is it good for? So we have an efficient BDD algorithm, so maybe we can apply this to our favorite problem of decoding, encoding and decoding over the Gaussian noise channel. Well, that's not sufficient, right? Because we do have an efficient decoding algorithm somehow, solving BDD, but we don't have an efficient encoding algorithm. For having efficient encoding, we would need to be able to sample short vector in this lattice, and that is something I have no idea how to do. And this is somehow what's paradoxical about this lattice. It's like when you look at other construction of good lattices, like the Barnes-Well lattice, I mean, we have very explicit knowledge about this lattice, and we know precisely which are its shortest vectors. So here the situation is kind of unique. We know how to solve BDD, but we don't know the short vectors. I guess there is one very beautiful and fascinating question is like, how do we solve, how do we kill this last missing log factor? And so we say, okay, so why do we lose this log factor in our construction? When you look at it, it's related to the fact that if you need n prime numbers, well, one of them is at least going to be of size n, or even n log n over the integers. So, I mean, if we want to solve this log n factor, we would like to have n primes and distinct primes, and they're all smaller than a constant. So obviously, over the integers, that is not going to work out. So maybe we need other algebraic structure. Maybe we could use function fill or something like this, but that is way beyond my algebra. So maybe this is for someone in this room. This is a problem for someone in this room. Thank you very much. I'd be happy to answer any question you might have.